Okay, so our actually next two speaker is Sebastian and Sathvik. They're from GitHub. And JuliaHub, sorry. JuliaHub. Oh. And, okay, I also use GitHub. Yeah. All right.
Hello. I will be talking about robust calibration with JuliaSim Model Optimizer. So first, what is JuliaSim Model Optimizer? JuliaSim Model Optimizer is a product from JuliaHub for parameter estimation and in general optimizing models to match data. And I will now go a bit into the problem that we're solving here. So for parameter estimation, we usually have we build complex models to describe real-world phenomena or real-world applications. And in order to have the models match reality, we usually rely on calibrating the models to data that we have collected. This process is not always very simple because for complex models you might have situations where it's not easy to feed the real-world data or the data that was acquired. And this comes from the fact that when we have complex models or very high-dimensional search space, the loss that one would use can be very complicated, like in this example. As we can see, there are a lot of local minima in here, and using optimizers can lead to getting stuck in such a local minima. For example, if we were to start in the blue point here, we can see that we have several possible scenarios of what a local optimizer might choose as the path to the solution, and we can see that it can get stuck in a local minima. What we would actually want is to be able to traverse these local minimas and get to the global minima. So what can we do about this problem? So what are our ways in which we can prevent local minima? One of them is, instead of trying to fit an entire trajectory at once, we can split the trajectory in multiple segments. So we'll have smaller trajectories that we need to fit, and the starting points of those small trajectories will have to be determined by the optimizer. Of course, now that we split the problem in several subproblems, we need to make sure that the problem that we are solving is actually corresponds to having one trajectory. And this essentially means that we have to ensure continuity. We can ensure continuity either via constraints in the optimizer or via a penalty function. And as we can see here in an example, we have the segments here. And here we are enforcing the continuity via penalty, and at the same time, we also have the cost of the difference to the data, and they are simultaneously optimized. And we can see as the optimization advances in the number of iterations, the segments tend to get closer and closer, and then they form a continuous solution, which then we can see that it also fits the data well, avoiding the problem of local minima.
Okay, so along with multiple shooting, we can have a prediction error method, which basically mixes data with the solution, and you can sort of nudge the current simulation towards the data. So mathematically, it's a ODE transform, which results in a very smooth, which smoothens the loss landscape. So this loss landscape you see on the left is actually a prediction error method smoothened loss landscape of the one which we saw in the first slide, second slide. So you can see that that loss landscape had so many minimas, but this loss landscape is so smooth that if you start at any point, it will eventually roll down to the actual solution. So this becomes important in complex systems where you have a lot of minima, and for complex models, you will have a lot of minima in higher dimensions, and this method can be used to sort of smoothen the loss landscape, which will eventually help in better calibration. So yeah, so this is a slide where, so the left side basically is the optimization trajectory without a prediction error method. You can see it's sort of stuck in the valley and sort of just stays in the valley and never goes to the actual solution. But while with prediction error method, it basically rolls down as easy as that to the actual solution. Okay. So okay, before going into code on how to use JuliaSim Model Optimizer, I just want to give a quick a demo of a JuliaSim Model Optimizer in action in JuliaSim. JuliaSim is a GUI, which is it's a product by JuliaHub, and where you can drag and drop components to build models, and you can also have simple and optimization analysis with it. I'll just give a quick demo of it. So you can see you can select all the components to build your model, and then you can use these components to actually build the model. But in this case, we have a pre-built model for demonstration. After you build the model, you can click on the analysis tab. I'll just take some time to explain what is this. This analysis is basically like a graphical user interface for Model Optimizer, where you can select what method you want and like what is the maximum number of iterations, what optimizer, and what type of loss function. And also, you can specify any data set. So this is like sort of compatible with JuliaHub.dataset, where you can upload it separately. So you don't have to upload it here. You can just mention the name and some specifications of it, like independent variable, dependent variable. Then you can mention what parameters you want to optimize and what are their bounds. Oh, sorry, what happened? Okay. Huh. Sorry. Okay. After that, you can click on simulation, which actually runs this optimization in the background. So it's in the cloud, so you don't have to worry about closing your laptop or something. Then you can come back, and then you can just plot the results and also the values of the calibrated parameters, as easy as that. Okay. So this was a quick demonstration. Now let's use Model Optimizer with some complex models. So for that, we are using it with JuliaSim-HVAC. So JuliaSim-HVAC is a proprietary HVAC library built by JuliaHub. So there was a talk on JuliaSim-HVAC like a couple of days ago, so I won't go into much details of that. So it's basically a library of components where you can plug and play to build HVAC models. For our demonstration purposes, we use a vapor compression cycle, which is a standard air conditioning cycle, which has a condenser, a compressor, an evaporator, and expansion valve. So let's do some interesting calibration with it.
Okay, so as we mentioned before, we have the vapor compression cycle, and what we're interested in is finding some coefficients that would represent a correlation between pressure drop and blast flow rate in a pipe in the evaporator and the condenser. And why we're interested in these parameters is because they are not easily directly measure. So in order to calibrate our HVAC model, we need these parameters, and we also have we might have experimental data collected from what is easy to measure from the actual HVAC system that we have, that we might want to improve or want to study further. So let me go a bit through the API here. So JuliaSim Model Optimizer works with models based on Modeling Toolkit, so it's built and integrated with the SciML ecosystem. So here we start by getting MTK model. In this case, it's an HVAC model, but it works with other MTK models. Then we define an experiment. So this is an instance for which we have experimental data. And the data can be any tabular data that we have, which has time series data for things that can be computed from the model. So predictions of the models or measurements from the model of any sort. We have a time span for the simulation, and then we can have integrators from ordinary DFQ, all the 300 plus integrators, and also all of their configurations, anything that you would normally specify with differential equations.jl or ordinary DFQ. And in this case, we're showing the PAM part, the prediction error method. So as was mentioned earlier, prediction error method is a model transformation. So it transforms the model that you have such that it adjusts it to the data. So the predictions of the model during the simulations are adjusted towards the data. And then we have to specify how are we going to compare the predictions from the transformed model to the data. And all of this information is encapsulated in this structure that we call experiment. So if you have multiple instances in which you might have collected data, so you have data for one particular experiment that you performed and another one, and you want to use both of them to calibrate the model to fit both scenarios, you can define however many experiments that you need. Then the next thing to define is the parameters to calibrate. So this is what we call the search space here. And simply it's just the symbolic representation from the Modeling Toolkit model. So the interface is purely symbolic. You don't need to worry about like indices or things like that, just like with Modeling Toolkit. Now, another thing that we need to specify is what are the lower and upper bounds and potentially the initial guess. If you don't specify the initial guess, you can deduce that from the defaults that are provided in the MTK model. Now, what we define is the inverse problem. So the inverse problem is the problem of finding what parameters of the model that are in the search space would correspond to a particular behavior of the model. This can be encoded by the loss function to how to match the data as closely as possible. The next step then is to define a calibration algorithm. And here we have support for several calibration algorithms such as single shooting and multiple shooting, and also so multiple shooting has also several configurations. We also support the collocation methods, and now I'm going to mostly talk about multiple shooting. So multiple shooting needs the number of trajectories. So this is in how many segments are we going to split the entire time span that we have data for and we are simulating for. Then we can provide a stopping condition, so maximum time or maximum number of iterations. So this runs automatically. So usually you want to ensure that, okay, I know that this will stop at some point no matter what, so you can check the results at that point, and if it's not enough, you can continue again. Of course, if the optimizer decides that the convergence criteria was found, then you will stop at that. But just to be sure, you can provide the maximum time. Yeah, I'm not willing to spend more than this amount of time running this. And then the next point is initialization. So this is how each of the segments, so as we can see, we have several segments for the trajectory, and we need a way to give the initial value for the segment. Since the optimizer will continue changing these values, it needs, depending on the optimizer, it might need an initial starting point. So in this case, we are using the data for initialization because the data can, in general, can be very helpful in providing us with a good hint of where the segment points might be. Of course, there might be other ways that might suit better in other scenarios. So we support several initialization methods for the segments. And next is how we want to parallelize. So we support, since multiple shooting essentially computes each of the segments in parallel, there is, I mean, this is a method that is very easy to parallelize, since the individual segments don't depend on each other. Then we can use multi-threading to parallelize them, or you can use distributed, or all the options that are supported in SciML. So we are compatible with that. And then how we enforce the continuity between segments. Again, you can use constraints, or you can use a penalty. And the last point is doing the actual calibration. Now, looking at the results here, we compared the single shooting method with multiple shooting with PEM. What does this mean? Is that we have the, as I mentioned earlier, you have the multiple shooting combined with prediction error method. Since prediction error method in itself is not a calibration method, you can combine it with either single shooting or with multiple shooting. In this case, we used simulated data with noise, as you might have seen on the previous slide. So here, the data has noise, so that we can also check, like since we know the ground truth, we can evaluate how well does method do compared to that. So we evaluated here single shooting and multiple shooting with prediction error method. And in this case, we have slightly better results for the multiple shooting with prediction error method. For the HVAC case that we're looking at here, this is how the loss surface looks like. We have some local minima that are in one region of the parameter space. But in this particular case, the optimizer is pretty good at dealing with that. So we get a slightly better result with multiple shooting, but we don't expect in this particular case like a huge improvement, because it wasn't such a drastic case as the one that we showed in the initial slides where single shooting would completely fail. Of course, this is just 2 parameters, so that we can also have plots and visualization for it. If we were to have tens of parameters, then there would be no way to visualize that. But when the dimension increases, it's much likely to have, in a high dimension, to have these complex geometries, where it would be much more hard for an optimization method to find the actual global minima. I think I went a bit fast, so if you have any questions, I think there's more time for that. But yeah, thank you for listening. And these are some QR codes. You can see our documentation if you're interested in trying this out. And I think that would be the end of our presentation. Thank you very much.
Thank you. Right, so in my line of work, what it is typically the case is that I have a, let's say, 5-dimensional system, 5 OTEs, but my experimental data is only 2 of them.
Yeah.
How do you, and the thing I'm interested in is how you handle the initial conditions for the unknown or the variables that are unobserved, particularly in the multiple shooting method, because, okay, maybe me as the user or the scientist, maybe I can cook up or I can smoke up an initial condition for the very start of the simulation. But now if you do multiple shooting, you have to somehow generate out of a magic hat initial conditions for the later stages of the simulation. How would this work, and even is it even possible?
So for the initial starting points, there are cases where if the observed that you have data for, if they are linear in the things that you have data for, then you can actually solve that and invert those. So there are cases in which you can invert that relation, and then you can find, so for example, if you have data for A and there is something that's an invertible function of that you have data for, then if that function can be inverted, we can do that inversion automatically.
No, I wasn't clear. I'm sorry. I have dimensions x, y, z of my dynamical system. I only have data for x and y. I don't have data for z. There is no function that can give you z from x and y.
Okay, okay.
So how would you initialize the initial conditions in the multiple shooting when the variable z has no data from you to infer a possible initial condition from?
In that case, I don't think you can compute that, but you can try strategies like if you do random initialization within an interval, or because you have a bounded interval that you're searching z in. And you can do a random initialization and do this several times and see how that behaves.
Yeah, okay. Yeah.
Any other questions? Then I think we have a shorter break. Let's give another round of applause for our presenters.